Okay, just to review, we figured out a systematic way of finding pi groups that develops a system of equations that we can use to solve for the powers that we raise our physical variables to. So like rho to the 1 power, mu to the negative 2 power. And then with these pi groups, we can then plug them into Buckingham Pi Theorem, and Buckingham Pi Theorem tells us the functional relationship between these two. It doesn't give us the actual function, but it does tell us things like f rho mu squared is going to be equal to some function of these. And that is useful because we can then do experiments where all we have to do is vary the Reynolds number, right? And measure this pi group. And then we can go back and figure out for some other situation what our Reynolds number will be and what this will be, and then we can apply it to our particular problem. So I did talk about how these are pi groups for the ball in a free stream of fluid problem. So we have a ball with some fluid coming at it with some velocity v, it has some diameter d, the fluid has some density and some viscosity, and we're measuring the drag force on the ball, and we're trying to predict the drag force on the ball for some prototype that we haven't made yet, right? So we ended up with different dimensionless pi groups than I had talked about at the very beginning of this, right? F rho over mu squared is different than the drag coefficient, which is f over rho v squared d squared, right? This is the same. The Reynolds number is still the same, but this is different. And the reason it's different is because we chose different repeating parameters. So in order to practice this, what we're going to do is we're going to try different repeating parameters for this same problem and see if we can get this drag coefficient out of this. This is one of the difficult parts about dimensional analysis because it's possible to find what we might call not meaningless, but not terribly useful pi groups. So in the case we did in the previous video, Reynolds number, super useful. Great, check that box. But force times density divided by mu squared is not super useful. The reason it's not super useful is because density and viscosity are both functions of the fluid. So let's say we have two situations we're trying to look at. One where we have a ball that is 10 times or twice the size of a human. So we have a human here, and we have a huge ball, and then we have another situation where we have a small ball. This is our model, and this is our prototype. This dimensionless group does not have any information about what makes these two situations different. And what makes them different is the diameter of the ball. So if we're doing an experiment with a model in air and we do an experiment with a prototype in air, the rho and the viscosity stay the same. All that would change is the force, and that's not super useful for us. We'd like to incorporate some information about the problem itself, like velocity and diameter. So all that to say, this dimensionless group is not as useful as drag coefficient, and knowing what's useful and what's not is simply a matter of trial and error in a lot of cases. So we're going to choose different repeating parameters this time, and let's start doing that. So instead of rho, d, and mu, which is what we chose last time, we're going to choose rho, v, and d as our repeating parameters. Let's check our three rules to make sure that these repeating parameters work. Our first rule is that all of our physical dimensions, our primary dimensions, have to be represented. So are they represented? We have mass, length, and time. Yep, check, check, and check. Great. Second, they have to be unique. Sure, density is not equal to velocity, is not equal to a length. Great, perfect. And third, they can't be powers of each other. And here, nope, none of them are powers of each other. We have length by itself, velocity, and density. None of them can be raised to the power and be equal to another one. So good, these meet all of our requirements, which means we can go forward and start building our pi groups. So the next step in this is going to be to choose one of the non-repeating parameters and build a pi group around it. I'm going to choose this one as our pi 1 and this one as our pi 2. So we're going to pick pi 1 and we're going to say pi 1 is equal to f times, oh, whoa, that skipped, f times rho to the a, v to the b, and d to the c. And this is going to be equal to mass length over time squared times mass over length cubed to the a power times length over time to the b power times length to the c power. And now that we have these written out, it makes it really easy for us to find our equations that we're going to solve. So let's write out our equations. And this would be a great time for you to pause the video and try to do this yourself, right? And then come back and see, check your work on with what I'm going to do. So we're going to do it in a little different color for some reason. Not sure why, but I like to use green at this point. So we're going to do mass first. We have 0 is equal to. Now we start with our physical variable that we're building our pi group around, which is our force. So that mass in our force is raised to the 1 power. So we do 1 plus m to the a is just a plus 0 plus 0 because there's no mass in our b or in either one of these two. There's no mass. So now we do length. 0 is equal to, in this case we have length on the top to the 1 power, so we're going to have 1 plus, now we have a length to the negative 3 multiplied by a, so we have negative 3a. Here we have length on the top to the 1 power, so it would be plus b plus c, because it's just length by itself. And for time, we have 0 is equal to, we have negative 2 here, so we have negative 2 plus nothing for a, 0a, plus negative 1b times on the bottom, so it would be negative 1 times b. And for c, we have 0. Great. These are relatively easy to solve for. A is equal to negative 1. Negative 1. Here we can find out b is going to be equal to negative 2. And if we plug these into here, we find out that c is going to be equal to negative 2. So our pi 1 is equal to f drag times rho to the negative 1, so that's over rho, v to the negative 2, so v squared, and d to the negative 2, so d squared on the bottom there, which is our drag coefficient. Great. Let's do it again. Let's do pi 1 or pi 2 now is equal to, now we're going to build it around our viscosity. So mu times rho to the a, v to the b, d to the c, which is equal to mass times length. Oh, sorry, I messed that up. Let's erase that. Mass over length times time times, and then everything is copied. This is why it's called repeating parameters. Everything's copied from this section right here, so we can just write it down. Mass per length cubed to the a, length over time to the b, and length to the c. Now again, we have rho v d. We know that this is going to end up being the Reynolds number, so we could solve this through inspection, right? But we're going to go through and we're going to do it the systematic way because we're less likely to make mistakes that way, for sure. Okay, so now we're going to write our system of equations. We'll do it in green. We have mass is mass. We have 0 is equal to. We have mass on top, so we have 1, and then everything else comes from this section. So remember, everything is repeated here, so we can just write all that down. Plus a plus 0 plus 0. Now for length, we have 0 is equal to negative 1, because length is on the bottom. So negative 1 plus negative 3a plus b plus c. And then for time, we have time on the bottom. So t, we have 0 is equal to negative 1 plus 0a plus negative 1b plus 0. Great. All right, so yep, we can solve this fairly easily, right? We find out that b is equal to negative 1. Oops. B is equal to negative 1 from this equation. From this equation, we see that a is equal to negative 1. And from if we plug everything in, we get that C is also equal to negative 1. So all three are equal to negative 1, which tells us that our pi 2 is equal to mu divided by rho v d. Now, this is still the Reynolds number. It doesn't matter that this is basically the inverse of the Reynolds number, but we could raise all of this to the negative 1, in which case pi 2 is equal to rho v d over mu, and it's still dimensionless, right? And the reason we can do that is because of what Buckingham Pi Theorem says, which Buckingham Pi Theorem says that in this case, our pi 1 is equal to some function of pi 2. So f over rho v squared d squared is equal to some function of mu over rho v d. We don't know what this function is. We're solving for it, right? So it doesn't really change the problem if we say, well, let's add a negative 1 here. Then we're able to say f over rho v squared d squared is equal to, let's figure out a new letter for this, some new function h of rho v d over mu, where h is just g with the raised to the negative power around the Reynolds number inside of it, right? It hasn't changed the problem at all. We're still solving for an unknown function using experiments. So we can then make these pi groups familiar to us, right? And the reason we want to make it familiar is because things like the Reynolds number are so well known and so useful that everybody, in a certain situation, you should be able to quote the Reynolds number and give somebody a feeling for what the flow around an object is like. So let's do an example, right? At Texas Tech, I had somebody applying for a job at a pump company, right? And this pump company would test a pump at a certain flow rate and alter it a little bit in order to fit some irrigation jobs, right? A lot of cotton there was being grown. And for a particular flow rate and a particular pump size, you would want to know what the Reynolds number is, right? And so if somebody is like, what's the Reynolds number for this pump? And you say it's 45,000, that tells them exactly what they need to know. But if you were to go, oh, the pi 2 for this problem, this particular pump in this particular station is 1 over the 45,000, so 0.0000, I don't know, 063, I'm making that up in my head, who knows. If you were to say that it's equal to this, they'd be like, what? That doesn't make any sense at all. The Reynolds number is always, for pumps in irrigation, is always higher than like 10,000, right? Or something like that, who knows. So because we have this, it's used so often, and because there's so much built-in inertia behind it, we always just report it as rho v d over mu and not the inverse, even though sometimes our systematic way of developing these pi groups gives us the inverse of the Reynolds number. Cool. Now, to be clear, on an exam, both would be right. All right. If you just stuck with mu over rho v d, that'd be fine. If you give us rho v d over mu, that is also fine. Okay. So these are really useful for these pi groups are really useful, and Buckingham Pi Theorem is really useful for the reasons we've talked about, which is that you can greatly simplify a problem into having just sometimes two variables if you're really lucky. Like we have the Reynolds number and the drag coefficient, these pi 1 in pi 2 that we had from just this example we just did. And then we could just do a single set of experiments and get a nice little curve. And then at any time in the future, we can figure out what our Reynolds number would be for the thing we're designing, move over, figure out what its drag coefficient is, and then determine what the drag force is on it very easily, right? But the other useful thing from pi groups is that they kind of give us a feeling for physically what's important for a problem. So we know for a ball in a free stream velocity, so a ball we've thrown, let's say, we know that the Reynolds number is very important. The Reynolds number is very important, right? The Reynolds number is equal to rho vd over mu, right? We could rewrite this as rho v over mu over d, right? This is a measure of the viscous force, right? And this is a measure of inertia. So what this dimensionless pi group tells us, if our Reynolds number is high, we have a lot of inertia. We have a lot of velocity or a very dense fluid. If Reynolds number is low, then viscous forces dominate, right? And so what we learn is that below certain Mach numbers, if your Mach number is very low, so we're not worried about compressibility effects, what is really important for fluids is whether or not inertia or viscous forces dominate, right? Other pi groups are also very useful. So for example, we can do the Euler number. EU is equal to pressure divided by 1/2 rho v squared. And this is a measure of pressure energy over, hopefully this looks familiar to you, you can recognize it, 1/2 mass times velocity squared is kinetic energy. So this is going to tell us what is going to dominate in a flow. Is pressure energy dominating? In other words, we have very high pressure but not much fluid flow, or do we have a lot of kinetic energy and not much pressure energy, right? Another one is the, I always mispronounce this, the Froude number, and it's equal to the velocity divided by the square root of gravity times a length. And this is a measure of whether or not inertia or gravity is important in a particular situation. Where this becomes important is, for example, in large, long boats, so like oil tankers or shipping container boats, where you have a very long boat, and these boats develop what's called a bow wave. I'm exaggerating it here, and the water builds up in front of the boat. We'll finish drawing our boat here. There we go. Well, here's some smoke coming out the top. It's a propeller, let's say. Okay. Anyway, the boats build up a wave of fluid as they move forward in the water, and the end result is that they're constantly going uphill, if you will, even though technically the ocean is flat. They're going uphill, and that becomes the limiting factor in the boat's speed and efficiency. So the Froude number, whatever, tells us whether or not the inertia of the water is dominating drag or whether or not gravity is dominating drag. Right? We have something we all know, which is the Mach number, which is equal to the velocity of something divided by c, where c is the speed of sound in the fluid. Pretty simple. It's just a ratio of speeds. We also have something called the Weber number, and there's tons of these numbers. I'm just doing you some of the ones that are the most common. The Weber number is rho v squared L squared over sigma. And if we take this L squared and move it down here, this becomes kinetic energy over surface tension. energy, or potential, really. It's a potential energy. It's a potential. Kind of like potential gravity. Surface tension is a potential to do work. It's not actual. Anyway, yeah, so surface tension, potential, surface tension, surface energy, surface tension, potential, sorry. So where does Weber number matter, right? Weber number matters when you have small amounts of fluid. For example, a droplet of water hitting a surface. The Weber number could tell us whether or not the droplet's going to break up when it hits the surface. If it's going fast enough, it will break up. If it's not, then the surface tension energy will dominate and it will stay together. Another example might be bugs on a surface of water. Is the speed of the bug large enough to overcome surface tension, and will it break through the surface of the water, or will it not, right? So Weber number is super useful. And you can do all kinds of different combinations of these, right? We could worry about whether or not pressure energy is related to surface tension energy or something like that, and these all end up. So there's literally hundreds of different dimensionless parameters that we could develop, but these are just some of the more common ones and what they mean, right? And so the takeaway of this whole section so far has been that Buckingham Pi Theorem is super useful for when we cannot develop easily models of a particular flow situation, right? And this is still true today, even though computational fluid dynamics is getting increasingly good. We still have situations where we still have to do experiments, either to validate our computational models or because the computational models, the situation is too complex for the computational models. So we don't have any way of predicting how the system is going to be except for through experiments, and experiments can be too complicated. In order to simplify the experiments, we use dimensional analysis to reduce the dimensionality of our problem through, for example, P, remember, is equal to n minus k, where n is the number of physical variables and k is the physical primary dimensions. So we reduce the dimensionality of the problem by the number of physical dimensions, so we end up with fewer variables that then we can use to do our experiment. And almost more importantly, these dimensionless variables are very flexible and not tied necessarily to the particular model or prototype that you're worried about. What do I mean by that? Well, I mean every ball that's moving through air with a Reynolds number equal to, say, 20,000 is going to behave the same. It doesn't matter what exactly rho, what density of the air, what velocity, what diameter, what viscosity. It doesn't matter what those are. What matters is the combination of these parameters, these physical variables. So we could double our velocity and halve our diameter, and we'll end up with the same Reynolds number, and we'll end up with the same behavior. And that's also very important to understand. And that's what makes these dimensionless pi groups so powerful, because you could tell somebody, oh, that ball that's moving through the air has a Reynolds number of 20,000, and everybody will go, I know exactly how that fluid is behaving. And I don't need to know anything else about it. I don't need to know the viscosity or what the fluid is. I just know how the whole system is behaving. Cool. So what comes next after this is we're going to practice using these in some interesting problems. And yeah, that's what we're going to work on next.